Yes, that's me. I just thought it was just like make sure your paper doesn't slide up. Oh, wait, I'm gonna ask, because I tried to find it on YouTube and I can't find it.
It used to be you.
Hey guys, just have your own class. You guys all do me one favor. You guys open up your slides on the first one. We have this recipe. Just go in there, click to the website, click on like this. You open up like that, and then basically on yours, it'll give you like the signing thing, and then just highlight whenever you're erased. So then if you don't have class, we have sports, this should be a general thing. Put them up there, and then based off these numbers, like right now this Friday is looking pretty good. Monday morning. Once I have all your data in there, I'll take the office hours and put them onto the list. With that being said, I know you already have somewhere, some people aren't able to make it. You can't make it to the scheduled office hours, just go Google Calendar, send me an invite, and then we can meet. Cool. Help me out with that. The other one that I need to do today is we're gonna go around the room, just tell me your name and then what's your favorite type of coffee, right? Let's do quick, we'll go around the room. All we need is first names, that way I can start to practice them. Just so you guys know, English is not my first language, so sometimes I might say your names a little bit too much in Spanish, and if that's the case, sorry, just let me know and I'll fix it, yeah? All right, Sam, what's your
Sam. Espresso.
Addison and a frappuccino.
I'm Gigi and a latte.
Gigi?
I'm Josie and latte.
Colin and espresso.
Camden, latte.
Kinsley and cortada.
Eleni, mocha.
Lenny?
Eleni.
Elizabeth, latte.
Parker and black.
Reese and latte.
Going.
Ariana and latte.
Jacob, Andre coffee. Give me a red.
Right, the caffeine, go.
It's better.
The caffeine, that's all I know.
Yeah. Andrew and caramel latte.
Abby, Dominican roast, black.
Aiden and I like cold brew.
I can't drink that anymore, man. That thing is too strong for me. I do it, I'll start shaking and sweating, it's bad.
Ethan and mocha.
Lila and latte. Asha and latte.
I'm Grace. I don't like coffee.
So back there.
Perla, iced coffee. Chloe, Americano.
Mazzy French vanilla drip.
One more time.
Mazzy in the drip French vanilla.
Summer, Americano.
Kindle, chai latte.
Thanks, guys. The coffee quiz is a little weird, but to be honest, I'm gonna use it next week when I start grouping you guys. So I'm gonna just divide the class up based on the drink. I see a lot of lattes, so I might have to split that up into two. And then black cold brew will probably mix you guys together. And then I think energy drink, no coffee, and chai latte. You guys might be a group. So Next time when we have the assignments, I'll basically share the PowerPoints with the questions, and then as a group, you guys will be responsible for answering them. I would prefer that you guys work through them as a group. What ends up happening most of the times is somebody grabs one question, somebody grabs another, right? And then you guys basically come together. But just make sure you guys double check each other's work because I graded it as a consensus. All right, thanks guys. And yeah, I already told you, I'm gonna mess up your names for the next like month before I start learning stuff. Now let's get to class stuff. All right, guys, I'm sorry, but today is the chemistry heavy day. Right? I warned you guys it was coming. I'm gonna try to stay on the surface. I tend to dive into it a little bit too much. I'll stay on the surface. The big thing here is you really need to understand how chemical interactions are happening. Right? So for that, we're really gonna dive in deep, figure out how the atom works. And based on how the atom works, we're gonna see that atom will bind differently, and behave differently with different partners. And once it's made that first bond, and it has like a way to bond to attach to something, depending on what two atoms are put together, they'll as a group have this group behavior that they can interact with other groups. So follow along. I think you're gonna end up making 2 tables throughout the day. So we'll start loading them up on that side and load the other one here. If you have any questions or you have blank spots, those are good things to come to office hours or hit the book again just to make sure you can hit the spots. All right, so in general, if we're looking at how we're built, these are the 4 big players, right? So carbon, hydrogen, oxygen, nitrogen. And they're the big players in the sense that our body has a lot of this, right? When it comes to these chemical reactions, because this is the majority of the molecules, I'm going to be talking a lot about how when these two partner up versus when these two partner up and how that changes their dynamics. Right? All you got to know is at this point is that's our percentage of how they're made, but we'll find them in different molecules. Then of course we have other elements that are found less often, but for this one, the one that I love the most is going to be phosphorus. So I'll be bringing this one up. But that carbon, hydrogen, oxygen, nitrogen, in pop quizzes, in multiple choice, I feel like even in exams, they love asking that question, right? So make sure you guys remember carbon, hydrogen, oxygen, nitrogen. Those are the big ones. All right. So let's look at how we define these guys, right? So for this part, we're going to start looking into the atom and see what basically builds it up, right? So this is going to be your first table. You're going to have your neutron, right? Proton, and your electron. So the things we're going to learn about this, guys, is one is that some of them have charge, some of them don't. So you guys look at here in the nucleus or in the center of what we find, there we have in brown the neutron. And when it comes to charge, no charge, right? Protons, that's basically shown in pink or in red. That's going to be our positive charge. And then in yellow, the thing circling around, that's basically our electrons. That comes in with a negative charge. So these things, I almost want you to think about them being almost like, they're like magnets trying to pull on each other. Positive and negative charges try to pull each other and they pull themselves in. But to be honest, the electron's spinning so fast, it basically just ends up spinning around it. Right? So this is the charge thing. The next thing we want to talk a little bit about this is where they're located, right? So we'll do location, neutron, proton. They're going to be sitting in the nucleus of your atom, right? So they're sitting in the center. So whenever you have, as we go forward today, and I'll tell you about how these molecules are moving with each other, we don't mess with that part. Right? That's going to be in the center, kind of put away. The thing we're going to really focus on is going to be our electron, which is going to be on the cloud. These are the ones that we're going to talk about today about how either if I have more electrons and you have less electrons, there's a chance that we might be attracted to each other. There's also chances, depending on how powerful we are about putting these electrons, I can steal electrons from you, or you can steal electrons from me. And that's going to be the big key of us going forward. Let's go. All right, so for this guy, the next thing we're gonna talk about is gonna be size of these things. Right, this is relative terms, it's large, this one's large, and then our electrons are small ones. So when it comes to us using this little code to tell us what we know about an atom, we're basically going to be using the information to let us know about what's happening with our neutrons and our protons, right? So if you guys look at it down here, helium, right? This one has 2 protons. So this atomic number actually is the one that represents what element you're looking at, right? So proton, this is your atomic number, right? So hydrogen has 1 proton. If you have 2 protons, now it's helium. If you have 3, it's lithium, 4 beryllium, and it's just walking down the periodic table, right? So the atomic number tells us what element we have. Then we have the neutrons, which don't have a charge, right? And these are ones that help you determine the isotope. And you figure this one out because this mass number represents the combination of protons and neutrons. So it's basically these 2 guys. Right? This is atomic mass number. Right? So with this one, in this case, 2 protons, right? We figure that from this bottom number. Because we're getting to 4, that means that the other 2 should be our neutrons. If it has more neutrons, it's technically still helium, it's just now a new isotope. And then you will judge that kind of by the weight. I think in water, they have like their own little fancy names, like deuterium, I think that's 2 extra neutrons, and then tritium is another version of still hydrogen, it just has more neutrons and stuff, right? All right, so this will tell us the element we have, this will tell us the isotope. This is kind of interesting or a little scary in the sense of like some of the isotopes, they have so many neutrons, they're a little unstable, so they'll fling them out. And then you have like this charged, or like non-charged, this molecule that go and hits other things, and that's like radiation. As elements degrade, goes down some of this stuff, and then they're super dangerous for us. But today we're going to be focusing on this guy. We're going to be keeping track of how the electron is working. So we're basically sitting here, seeing how this is going to be shared, moved around between partners. All right, so this is our table. I'm going to go through it horizontally and then vertically. But here we need a little bit of extra information of what's going on. All right, so the little gray circle basically represents our nucleus, right? So in there you have your protons and your neutrons. That yellow dot represents your electrons spinning around it. So depending on what sphere, or what shell you're in. So this is first shell, these 2. Our second shell is basically this row, and our third shell is this row. We'll be seeing that as you kind of go up from left to right, you're getting more electrons added to you. What ends up happening is that the thing you have to know from here is that in your first shell, the stable state, where it's like, hey, it has electrons that it's spinning around, but they're actually in a happy environment, it's going to achieve it when it has 2 electrons. So this is when your atom is going to be stable, right? The difference is once you get to the second shell, and then your third shell, is now 8 electrons is the place where these things are going to be stable, right? So they're going to be trying to push themselves to these states. So helium, neon, fluoride, you can see 2 on the outside, 8 on the outside, so that's happy. 8 on the outside, this is happy, right? Then from there, we're going to see that you're going to have 2 different ways of getting away from this, right? If we move from neon and we move it towards the left and we hit fluorine, we see we have 1, 2, 3, 4, 5, 6, 7. Right? So this thing is short 1 electron of being in this happy state of like it's balanced, everything's good. So these, because they're up here, they're more likely to try to pull in an extra electron, and then they'll be in their happy state, right? On this side, so imagine we're going neon and we're kind of looping around, coming or like moving to the right of the neon, which moves back over here. What ends up happening is this one, our third shell, you can see now we have an extra electron. Now it's in a whole new third shell by itself, right? So it's harder for it to try to gain 7 electrons to be happy. So what it actually ends up doing is this can donate that electron, and then it goes back to behaving like it's in this second shell, which has 8 electrons, so it'll be stable. So the big thing is here, these, like you can tell on this row, the shells is when they're stable, right? 2, 8, 8. If we move this way, these ones are more likely to accept an electron to become stable. If you kind of basically go all the way around and start on this side, this is likely to drop off 1 electron, 2 electrons, or 3 electrons. And that's the way it's going to be able to achieve its more, like make the inner shell be the stable. Does that kind of make sense? Yeah? No? Any questions? Yeah.
So are helium, neon, and argon, are they always stable? Can you ever have like them without a full valence shell?
I think you can make them do it. Normally that's where like with the bio stuff, it's like our bodies make proteins and enzymes that'll literally grab these molecules and kind of smack them into each other to make them proteins. But the one I'm going to right now is I'm gonna show you that basically this group here has this thing called like electronegativity. So it's like super greedy and it loves to pull electrons. So these don't have that much, so they're actually more easily stripped from them. Those are going to get non-reactive stuff. That's going to decrease it. All right, everyone feeling comfortable with the table? Yeah? All right. Let's go. So this thing that we're talking about, it's a big keyword, valence electrons. I know people love to bring it up, right? But that all it really means is we just care about what's the outermost shell. So in this case, neon, because it has 10, we just care about the outer one. Here's our 3 shell. That would be that valence electron would be down there. And for chlorine, you can see it's the outside one. So here there's atoms with the same valence electrons that's in similar chemical behavior. Is basically what I was telling you guys like right here, right? These two are waiting, they want to pick something up, an extra electron to be stable. Those groups down there, they rather get rid of an electron so they can get their happy state or their stable state. All right. So now we're going to be looking at how 2 atoms can actually come together and interact with each other, right? So for this, again, this one has the first shell with only 1 electron. So that's going to make this one want to reach having that second electron to be on a stable state, right? Because it has this incomplete valence shell, like it doesn't have the 2 that it needs yet. Oxygen, right? Remember for this one, we're saying it's trying to get to 8, it's already at 6 on the outside. So it needs 2 more, and technically it'll reach its balance state. So this will be the things that will drive the reaction, how things glue to each other. Right? So in this class, I'm gonna make you guys learn this one. Oxygen, hydrogen is gonna be a big one you're gonna have to know. And then carbon to hydrogen is gonna be another one. Those are the ones I'm gonna bring up throughout the course. This section, I know it's gonna be on the FINDO, and for sure it's gonna be on the COPS, because those are the molecules everyone loves, right? So let's bring this up. So now we're gonna be talking about how do these bonds work. For this one, this will be our second table. These are the bonds we're gonna go through right now. So for covalent bonds, we have 2 types, which is gonna be polar and non-polar. Then we have ionic bonds. These 2 are the powerful things. Down here, we have the weaker bonds, which is the hydrogen bonds, and the weakest is the standard bonds. And we're really going to walk through them right now, just going how these electrons are behaving. Right? So with a covalent bond, basically what they're doing here is they're sharing electrons, right? Like I wish they had color coded this a little bit different. So 1 hydrogen, 1 electron. In order to fill a shell, it needs 1 more. So what it'll do is this hydrogen, let's say this could be its electron, and this is the electron that belongs to this one. When they come together, right, what's going to end up happening is these 2 electrons are going to spin around this atom, and then randomly spin around this one. So when the movement of these atoms is kind of going back and forth like this, it makes this hydrogen feel like it has 2 electrons. So for its ability to sense, it thinks it's at 2 electrons. It's like, hey, I'm happy, I'm stable, this is the place I want to be. Same thing with this hydrogen. So they're able to share it, and it's going to be their way of being attached to each other. The electrons will leave me, spin around the other atom, come back, spin around myself. And this will be that first level bond of like two atoms grabbed onto each other, and we have this super strong bond. So here's a little diagram of them coming. It did it once. Give me 1 second. All right. So it's too fast. I need to slow that down. But as you guys can see there, right? Hydrogen, we saw it bring in 1 electron each. They glue themselves together. Chloride, that's the one that's missing 1, right? It has 7. And that's where they'll be sharing 1 electron from that atom, 1 electron from this atom, and that'll be the thing that's going to be shared to make that happen. Carbon, this is one of the ones you're going to hear about it in all my classes, in all biochem, because it's basically like the foundation of all the molecules kind of build up onto it. And one of the big benefits is that it has this, where it has, it only has 4 electrons itself, but in order to complete its shell, it needs 8 electrons. Right, so it means it has to get 4 more, and that gives it the ability to bind with a lot of partners. Right, so here you can see it's going to be down to 4 hydrogens, and then now the carbon will be stable because it feels like it has 8, and then your hydrogen is going to feel like it has 2, so it's going to be happy with it. The other type we're going to look at is, this is another big one, it's going to be your water. So again, water has 6, we're missing 2 electrons. When they come in, now the hydrogen feels like it has 2 electrons. Hydrogen's happy, oxygen feels the 8, and it's going to be stable. So that'll be like a little group. All right, so I have a weird analogy. I kind of think of atoms almost like people. So then if we thought about this in the class, this could be like, let's say this is the tennis team, right? It's like, hey, they hang out together, they interact, that thing of they work out together, they might end up eating together, they might study together. It's a thing that kind of holds them together and they're a unit. And that's going to be that electron, like paying each other attention. That's their hangout. But it's a permanent thing where they're actually sharing electrons, so it makes them really stick with each other. After this, I'm going to show you non-covalent bonds, and then you'll see how there's going to be a little bit of a different type of level of behavior. All right, so let me break down these covalent bonds into 2 smaller subcategories. So, oh, sorry. I rushed. Give me a second, guys. Yeah, I'll do this one, then I'll go back. All right. So when it comes to the electrons, when they're being shared, the first samples you saw were hydrogen, hydrogen, which means those 2 only have 1 proton and 1 proton, so they have that much energy to pull in electrons. But based on what proton you have more of a positive charge. It changes your ability to strip things. All right. So if you guys ever see these arrows on my presentations on the right, I'll put extra information to the side, kind of like this. But anything that's not on your slide is not going to be on the test. Right? It's just a little extra background. So you guys can kind of ignore it, but to me, it does give us a little bit of extra background. So we get a quick look at this periodic table. Here we've color-coded it based on how much the it's being called electronegativity, which is how much are they going to be able to pull in electrons, or like their power. The only thing I really want you guys to notice, you can kind of like zone out and don't care about it, is like this row doesn't have any electronegativity. So remember, they're stable, right amount of electrons, protons are happy. This top right corner is where they're the most electronegative, right? Because they have the most amount of protons and they're missing that last electron, so they're very likely to steal stuff away. So these are basically like greedy in the interaction. Going the opposite way, right? So to the left and down, going this way, those are less electronegative. And in that case, they don't have that much power to hold on to them. So they're more likely to lose. Does that kind of make sense? Yeah.
So you're saying the lower the electronegativity, the less likely they are, or the less stronger they are to be able to take from others? Can you just go over electronegativity one more time?
Yeah, so it's like all right, this is a bad one, but this is the way I remember it. So it's like, imagine these are like couples, right? You know how there's some couples who are like, they're both pretty funny, they both talk. That'll be their electronegativity, right? The funnier they are, the more attention they get. If they're both either high or low, right, but they're hanging around exactly with themselves, it'll stay non-polar. Right? So oxygen has a huge electronegativity, but if it's trying to hang out with another oxygen, because we both have the same power in doing this, the electrons are going to feel like, all right, so it's going to be fair between the two of us. The difference is going to come in when you hang out, for example, oxygen and hydrogen. That's my favorite one. I'm going to talk about this like at least in 15 slides. Come going forward. Right? In that case, it's oxygen, it's in red, super electronegative. It loves to steal the electrons. And hydrogen, you see it's 2.1, it's not that strong. So what ends up happening is oxygen will kind of behave something like this. It'll be electronegative. So what it's going to do is it's going to be pulling more of the electrons. And then my way of kind of thinking about it is like, when you think about the amount of time the electron spends around the atom, in this case, it'll be like, hey, you might spend a second or two here, a second or two there, a second or two here, a second or two there. That's my rough thing. It's actually happening like super fast. But let's just imagine the seconds in there, right? A second here, so they're pretty even. In this case, the electronegativity of that one is going to make the atoms hang around it. So the electrons will be spinning around there, let's say 10 seconds, and then it might go back for just 1 second. But because they're hanging out there so much, this atom and other things in the environment kind of look at it, they'll think, hey, there's one extra electron here. Because there's one more extra electron, we have that extra negative charge in this. Right? On this side, it doesn't get that much time with the electrons, which will give this side a little bit of a positive charge. Right? So that'll be the non-polar and polar. It's all coming from the differences between two atoms interacting with each other. Right? So with that being said, have you guys ever been like at a dinner with a group of 4 people? What's up?
I had a question. So are all non-polar covalent bonds, are they just the ones where it's the same element binding with each other?
Good question. You can have them happen like this. The other one that I'm for sure going to bring up a lot is going to be carbon and hydrogen. So this is a 2.1, 2.5. Even though they're different atoms, their ability to pull things is basically pretty similar to each other. So their electrons will spend at the time here. So they'll be part of this group. So,
But so most of the time, this is going to be the same element.
yes, but in this class, to be honest, we're going to be doing more of that.
Okay.
Where 2 atoms that have different charges will hang out each other, but they're so close where it's really technically it's the same thing. I think in one of the quizzes I'm going to give you guys, I'm actually going to give you a table. I can't remember the exact numbers, but it's like you subtract one of these from one of these. There's a range. If that difference is bigger than a certain number, it's a polar reaction. If it's smaller than that, then it's a non-polar. So at that point, kind of the atoms don't matter, just the charge difference. All right, so let's go back to this thing. So again, difference in the electronegativity is going to tell us where the electrons hang out. And then you have your non-polar. This guy should have you go on time. Your polar covalent bonds, they're going to be hanging out differently. One side's going to be charged, the other one's not. This is super important in bio. I'm going to bring it up maybe a few more times because every time we talk about how things interact, what ends up happening is this pair of electrons that are kind of working will be able, let's say we have another hydrogen, this would be like another chloride. The positive charge of this hydrogen will kind of make it hang out around the outside, kind of like that. They won't share electrons between these two. It's just that we know that this negative is positive, so they'll hang out. So that means that polar molecules normally want to hang out with each other. Non-polar molecules, because they don't have that super strong pull, if this atom, you see this guy's floating around, it'd rather come hang out with this guy than to hang out with that one. Right? Because it won't have that little charge to kind of help it calm it down. All right, this one is my favorite one, and we're going to bring it up all the time, like this week or next week. I literally have one whole class just dedicated to water. Right? So here, we follow our rules, right? Here's our oxygen. Remember, this one is super electronegative. It's really efficient at filling electrons. So it's going to be stealing, or it's going to be using the electron pair that these two are sharing more often than our hydrogen. So this will get a negative charge here, a positive charge there, and a positive charge there. As that polar covalent bond happens, this leads it to this part and this part, make it super useful for interacting with other molecules. Right? All right. Now, we basically walked ourselves through non-polar covalent bonds, polar covalent bonds. Now we're jumping ship. We're going to go to ionic. The difference is these share the electrons. This thing actually takes it away from the molecule. Right? So in this case, there's a little bit of terminology, so I'll make sure you guys emphasize these two words, anion and cation. So the positive charge, so they start off something like this, right? So in your kitchen, this is basically salt, NaCl. It's a little crystal. These things are kind of attached to each other, right? When we add water, then it allows it to do the reaction. What's going to happen is the electron from here that's going to go to the chloride, and these two can dissociate from each other. So they no longer have that interaction or bond to themselves. Like those would be free floating. In that case, this is the big difference, right? Na. So you can see Na is the third row all the way to the left. So that one has one extra electron, but it has 12. It has 12 protons, right? So it should have 12 protons, 12 electrons. The moment we use the electron, we still have our 12 protons. So that means that we have 12 positive charges and only 11 negative charges, and that gives us that charge to the molecule. This one ends up getting the extra electron, and that's what gives us the negativity. And then here's the little diagram of kind of how it's working like. That'd be a little crystal of salt. Normally that bond is the strongest, they'll be grabbing onto each other. The moment you add the water, remember you'll be bringing in that negative and positive charge, and these things will reorient themselves to go interact with the molecules. Right? So our positively charged molecule is going to hang around with our water because it has the oxygen in the water because that's the negative side. Our negative molecule is going to want to interact with our hydrogen because that has the opposite charge. And that's the way they're kind of basically going to hang out with each other.
So are ionic bonds weaker than covalent bonds?
Let me double check the way it works. If I remember correctly, they're stronger when it's in a crystal form. The moment you bring water into this thing, these things fall apart because they're able to do this. But I feel like I thought it was a chart that I saw where it was like the energy is like it drops off. But I'll look it up and I'll add it to the right of the slide. Yeah. The chemical interactions. All right. So this is the powerful stuff, powerful interactions. I need to go back for a quick second. Sorry about this, guys. So this is just a quick, while we're still sharing electrons, there's, you can share different amounts of electrons, right? So this one, just remember, there's going to be 3 words. So for the single bond, right, it's like this hydrogen, each one of them is bringing 1 electron into the picture, and that's going to be, they're sharing 1 electron pair, right? So it means that 1 from each. There's 1 electron pair or 2 electrons in this. They love writing the questions when they tell you how many electrons versus electron pairs. So make sure you guys write those on your notes. So, and then 1 electron pair, aka 1 electron from each. We normally do our annotations to look something like this. So it'll be a little single dash. That means we're sharing 2 electrons. Here we're looking at oxygen, right? So oxygen needs 2 electrons to be happy. In this case, each atom is going to be doing 2 electrons by themselves and 2 electrons. So here we have 2 electron pairs. And when we draw these, we're basically drawing with a double bond. And then the triple bond, right, is just 3 electron pairs. 1, 2, and 3. That makes sense? Pretty easy? Yeah. All right. And if you guys, when you guys take OChem and chemistry, they're going to give you a lot of math because based on how they're sharing the electrons, it changes their arrangement. I'm gonna try not to go into that because otherwise it's a bunch of angles and I don't want to get people lost. But if you have any questions about that, you can bring it up to me. But for now, we'll just say know the 3 bond types and we'll be all right. All right, cool. All right, so that's the end of the powerful stuff. Now we're gonna jump into the weaker stuff. So the other ones, they to me, in my head, I almost think they're a little bit more permanent. Like again, people in the same tennis team, right? You're gonna hang out with each other. As you go through the years of college, you guys are probably gonna be hanging out for almost the whole time, right? So that's the big interactions, but it's a little bit longer. These weaker bonds, I almost think of them of like you guys in this class, right? Next semester, you might sign up for a different class, you might change, the times of the morning, afternoon, and that means that your association is gonna be this quick little thing, and then it separates. Right? And that's what we're gonna be looking at right now. So in this case, my favorite one, hydrogen bonds. That's the big one, right? In this case, this is a group of friends, right? There's your electronegativity, has a lot more electrons. These are positively charged. Their electrons stay with them, right? They're not moving anywhere. This other molecule is gonna come in, and because the oxygen has all those electrons hanging around, it'll make these two attracted to each other. But they'll just be in the proximity of each other. They won't actually swap an electron back and forth. Does that make sense? Right, so it's just the charges are bringing stuff together. This is one of the favorite ones. Like I said, we're gonna go over it pretty heavily. So in this case, the big thing I want you guys to notice is the hydrogen bonds. It's polar covalent bonds that are happening here are setting up this interaction. Right? Polar will want to interact with polar. And in van der Waals, it works for the non-polars. So in this case, I almost want you to think like, if that was a hydrogen atom, and like we saw before, two hydrogen atoms can hang out with each other and the electrons are going to balance pretty evenly. In this case, this is one of the weakest ones because what ends up happening is that just by random chance, as the electron is spinning around this, like for like a fraction of the time, it'll be like, hey, it hung out on this side too much. So that means that for that little fraction of time, this thing feels like it has like a little weak little positive charge, right? If another molecule is going to come in, it might have a chance that, hey, if my negative charge is near the positive charge that one, will be attracted for that fraction of that second. And then the electron keeps moving, at which point I lose that interaction, right? So this thing, if you look at just measuring one atom interacting with another atom, it's super weak, like it's the weakest thing. But the crazy thing is, or the trick that our cells do is that they actually put stacks of these, like they actually organize them into like tubes, imagine this, and like every 3 inches, there's one of these little pockets or one of these little structures, which means that if another molecule comes in and we have another long stack, we have to break all these little bonds in order to separate this thing. So the bond itself is weak. Because we put a lot of them together, we can get power. And that's kind of what they're really showing off with this guy, right? So this guy doesn't have like, it has like a sticky surface. It's not like putting a vacuum. It's just that the interaction, that van der Waals interaction of non-polar stuff is enough energy across that whole surface area and lets it kind of grip onto the surface. Yeah. All right, cool. And another big point that we're going to be talking about as we go forward is going to be molecules. So later on, I'm going to get super into this thing called functional groups, which just basically means does it have a group of oxygen, does it have nitrogen, does it have phosphorus? And what ends up happening here is that in water, we saw that all 3 elements have charge spots, right? So they're all polar. Once you get into bigger stuff like this, you can see here it's 1, 2, 3, 4, 5, 6. So this is a 6-carbon ring. These white things are hydrogen, right? Carbon and hydrogen are pretty close in electronegativity. So this, technically this section is going to be non-polar. But part of this same molecule over here, when you see all these red things will represent oxygen, what do you guys think we expect back there? Or how's it going to behave?
Negative charge.
Negative charge, right? So it's going to be sitting there stealing the electron, not stealing, but borrowing the electron more often than not from the carbon, so it'll have a negative charge. So we can have bigger molecules that have non-polar and polar regions. And basically when we get into this, like even the cell wall, that's the trick it has. These little spheres on top are the hydrophilic or stuff that loves polar. The center stuff is those stacks I was talking about that are non-polar and they'll stick to each other just with that little random electron bounce. All right, so for this one, don't memorize the atom, don't write the names. It's just a big general thing. All right, and then The other thing we're gonna be bringing up is I will be doing drawings of chemical reactions. So for this, it's, make sure you guys feel comfortable with these words, like reactants and products. So reactants are all the things you put in. After the chemical reaction happens, you basically produce your product. In this case, we're showing that the chemical, this thing helps us let us know that the reaction is going this way. The other thing you gotta know is the size of this arrow talks about how much is driven towards that side. This is the simplified version. Later on, I'll show you, I'll start adding some that have, like, for example, a big arrow going this way and then a small arrow going back. And then what's happening there just means that on the forward arrow, when these kind of bump into each other, this one has such a negative charge, it might steal the charge, like an electron from this group. You're gonna start stripping it. And when it does that, it'll help us make the water molecule, right? But just like that happens, these two might crash into each other like this, right? Like hydrogens to hydrogens, and the hydrogens will stick to each other. And then the oxygens basically are by themselves, they'll move back, and the reaction will go back. Yeah. So the three keywords, those arrows are the big thing. And then basically the thing that, sorry guys, the thing that we do is that these chemical reactions are not super efficient. They don't happen fast. They take time. These things have to randomly bump into each other, and they have to do it at the right orientation. Our cells have proteins, what I'll show you guys, they really grab things, put them in the right orientation, and kind of smack them into each other to make things happen more efficiently. And here I'm just showing you my favorite one, which is like what plants are doing, which is we have carbon, 6 CO2, right? That's what we're breathing out. So carbon, 2 oxygens, and we have water. The plants are able to use light to power a reaction where they start gluing these carbons together. Right? As they do that, they basically are able to go from these low energy molecules to this guy, which is a super high energy molecule. We can push it forward. After the reaction, this is the one that we can bring it into our cells. We'll cut it up. We'll basically get the energy. But I'm not going to go too much into it here. Once we get there, I'll show you guys exactly how we're going to be cutting and building these. For this though, let's take a quick second because I'm going to draw it a lot. I'm going to be lazy when I do it, but I want you to know glucose. I want you to know these numbers and this little drawing, right? So for this one, the way I draw it, or you're going to see me draw it the most often, it's going to look like this. Right? So whenever you see me draw this, I'm thinking about glucose. Now, if I was in OChem class, they'd expect me to draw this, I'd have to draw more bonds. So every time you see a place where it bends, this represents that there's a carbon. So this will be our 6 carbons. At each one of these carbons, what we're going to find is that the carbon needs to be stable, right? You guys remember how many interactions for carbon to be stable? Any guesses? 4, yeah. 4, right? Currently, it only has 2. 1 carbon, 2 carbon. So here what's going to happen is you're going to have one side that's going to interact with the OH, and the other side's going to interact with a hydrogen. And as we go to each of these carbons, we're going to see the same thing. An H, OH, and then an H, OH. Carbon, 4 partners, it's happy. Hydrogen, 1 partner, it's happy. Oxygen, 1 partner here, 1 partner there. Oxygen's happy. Hydrogen, 1 partner, it's happy. All right, that makes sense? All right, so glucose, I want you guys to memorize it because every carbon has one hydrogen here, 1 hydrogen there. It ends up having twice as many hydrogens as carbons, right? And each carbon only has 1 oxygen, so you get that O6. People love putting this thing on quizzes to ask people when they're like, hey, can you tell me the difference between sugar and a protein or sugar and some other molecule? So if you see that ratio, you know you're talking about sugar. Some people, what they'll do is they'll bring this down to a 5, and then it's going to be 10 and 5. Yeah. So be ready with that one. Cool. All right, so my little exercise you guys should probably do after class, just to refresh kind of what we did over the whole lecture is go over these 4 bonds, right, technically 5, because there's 2 different types of covalent bonds. Go through them, think about like their strength, relative strength, like what's strong, what's weak. And then the other one is what's happening with the electron. So down here in a covalent bond, what do we do with the electrons, right? We're sharing them. Like you hold them, I hold them. If it's a polar reaction, that means that I'm greedier and I'll hold them more often than you do. If it's non-polar, that's a good balanced relationship. They'll share them evenly. Ionic bonds, what happens to the electrons there? Transfer, right? So it's like here we're stealing it. It's like, hey, you go your way, I take my electron, goodbye, right? And then how about hydrogen bonds? So that one, it's neither, right? So it's not stolen or shared because they stay on each of the molecules. It's just the charges are how they attract them together, but they're not sharing the electrons. Yeah. So then this one's based off of polar stuff. This is based off non-polar stuff. Any questions? All right, don't cheat, but the table is to the right of this. What else is in there? Strength and electrons, yeah. Try making your own table, see how you go, and then once you're done, check it against this little table on the right to make sure you're on the right page. Yeah. This table, I haven't made it yet, the first neutron, protons, electrons, so hopefully you have that in your notes. If I have time today, I'm gonna go back and I'll add it to the right of that slide. Any questions?
I have a question about, not necessarily about this, but you had said that you were recording the online lectures and putting them on YouTube.
Yeah.
What channel or where can we like get access to those?
Let me, I didn't upload Mondays yet, but once I send you one link, they'll kind of link, they'll be inside of one little video thing.
Okay,
Yeah.
great, thank you.
And FYI, that thing's on recording. The moment I get in here, I start setting it up. Last year I had an issue where when I was still setting up, I'm quiet. If you're talking, just so you know, that thing will go in and find you. And it'll like record you talking. So yeah, just so you guys, FYI, that's gonna be at the beginning of the videos. Any other questions? Good to go? All right, see you guys on Friday.
Was that that meeting with Jacob?
Yeah, I usually don't.
I
really don't like
Office hours.
I have to go. I don't know.
Have it open
So,
to get the most people to show up to those. Like, to be
I
able
would,
to-
like,
then-
I'll tell you when I'm heading over.
So it's like usually something comes up.
I'll
and you
probably
can
be
just go to Google, you kind of just search my name, it'll show you literally on my open.
So,
And then, yeah, let me know when you're
Show
done.
it.
You see him on Facebook.
Let's do it.
No. Sorry.